Okay, so it's 9 o'clock. Let's start. So last time we talked about the Schrodinger equation. So I gave you a rationale how Schrodinger formulated the equation in the first place. So there are many ways to formulate the equation governs the behavior of the wave function. And we use a simple way that comes from the fact that we can write down the total energy of the system, or so-called Hamiltonian of the system, in two ways. One, by taking the time derivative, the other by taking the space derivative, which you can get the momentum. Okay, so let me write it down again. The Schrodinger equation. Okay. Okay, so the time-dependent part is IH bar partial t. So take the partial derivative with respect to time. Then we added the h bar, we added the imaginary number so that we can get a real number. And so this is the Hamiltonian operator. And that applies on the wave function. It's equal to the other way to write down the Hamiltonian operator is by starting from the momentum. So this is the kinetic energy part of P squared over 2m. So P is minus IH bar del, and I squared gives us this minus sign. And then plus the potential energy part, V as a function of R. Okay. And this is equal to times the wave function again. Okay. So this is the Schrodinger equation. And so in quantum mechanics, especially non-relativistic quantum mechanics, you can treat this is the starting point. So it's like the Newton's equation in classical mechanics, or the Maxwell's equations in classical electrodynamics. Okay, and the much of the rest of the quantum mechanics we talk about is based on the solution of this Schrodinger equation. So so today's topic is Born's role and the statistical or so-called Copenhagen interpretation before we get to this Schrodinger equation. So what does the Schrodinger equation give us? So as I mentioned last time, so there are two steps of the story. So one is first, how given particular system, how do we find out the wave function? And the solution will be this Schrodinger equation. And the second step will be, if we know the wave function, then how do we compare the predictions of the wave function of the quantum to the real experimental measurements? Okay, so this the first step is given a particular system, how do we find out the wave function? And we do that by solving the Schrodinger equation. If you look at the Schrodinger equation, what is the input? Okay. What do we need to know in order to solve the Schrodinger equation? So if you look at this equation, what is the unknown? So the V of R, right? If you want to solve this differential equation, then we need to know the potential. So the interaction. V of R. To give you one example, if you want to know the behavior of one electron, then we need to know what kind of force does the electron feel. So whether you put the electron in a, let's say near a proton, or whether you put the electron in another form of interaction potential. Okay. So we need to know the interaction potential before we can solve the wave function. So V of R is the input. So this is actually very similar to classical mechanics as well, right? So in classical mechanics, like Newton's equation would be so F equal to ma, right? So force equal to m times acceleration. So the force, you can write down the force as the derivative of the potential. So overall, we all need the interaction potential as the input. Okay, so that's the first thing we need in order to solve this sorting equation. Then what about others? If you look at this equation again, so it is a partial differential equation. Second order in space, we have the del square there. So I have to partial derivative with respect to space twice. And it's first order in time. So it's partial t, so only first order in time. Okay. So when we solve a differential equation, then we need the initial condition. Same thing like a Newton's law. So Newton's law, F equal to ma. So we need the interaction potential. In other words, we need to know the force. Then after that, we have a force equal to ma. A is x double dot. It's a derivative of the space to the second order. Then we need two initial conditions. One is at time 0, where's the particle? And second initial condition is at time 0, what is the speed? So we need the x dot and x at time 0. Because Newton's equation is second order in time. Here, the sorting equation is the first order in time. So we only need one initial condition. So we only need to know the wave function at time 0, at t equal to 0. Okay? Of course, this is a function. This initial condition itself is a function. It's applied at all the space R, but at time 0. So these are the input. So these two are the input. Okay. So in order to solve the sorting equation, we need to know the interaction. We need to know the initial condition. Okay. In fact, this is no different from classical physics. It's the same as Newton's law. We require the same input, with the exception that now we don't need the velocity of the particles anymore because the sorting equation is the first order in time. Okay. So then, given that, what is the output? If we solve the sorting equation, what do we get? It's a wave function, right? The wave function psi at the function r and t. Okay. So now the part 1 of the problem is solved. Given a system, now we have a way to solve the differential equation, the sorting equation, and find out the wave function. So we'll give you a couple of examples this semester, and in fact, we'll talk about a lot more examples next semester. So a lot of the differences of different quantum mechanics problem lies in those interactions. So for instance, the system relevant to us would be atomic model and nuclear model. Okay? So they're very different. The nature of interaction is very different. For atomic model, we use hydrogen as a model system. So it's basically when you put an electron next to a proton. So it's a proton-electron system. Okay. So for atomic physics, so atomic model, the typical model is a proton-electron system. Okay. So in other words, this is a hydrogen. Then the interaction potential is Coulombic. It's a Coulombic. So electrons and protons attracting each other by this Coulomb interaction. And Coulomb interaction, V of R, with some coefficient is proportional to 1 over R. And we can plug this 1 over R in here and solve this sorting equation. Then you'll be amazed that the simple equation will give us the orbitals of electrons, their energy, and explain everything about the hydrogen atom very precisely. And another model relevant to us is a nuclear model. So not only are we interested in the structure of the atom, especially in this department, we're also interested in the structure of the nucleus. So the nucleus, if you think about a simple example, just like the hydrogen model, we can also solve a simple model system. So in that case, we pick the deuterium, so the core of the nucleus, the core of the deuterium, as example. So that would be a proton-neutron system. Okay. You think about the nucleus of deuterium, so-called deuterium. Then what is the structure? How can neutron-proton bind with each other? In this case, the interaction is not Coulombic anymore. The neutron itself is neutral. So the interaction is the strong nuclear force. Okay. So the range of interaction is much shorter than the Coulomb interaction. But the physics is the same. We still use the same Schrodinger equation to describe the nuclear structure. Okay. In that case, we assume the interaction is a very short range, but a simple square potential. Okay. And then we can put the square potential in, and of course the square in a 3D-dimensional square, and then solve the Schrodinger equation, find out the wave function and the corresponding energy level, etc. Okay. So these are the two examples relevant to us. But before going there, we need to introduce a few more math and even more understanding of quantum mechanics before we can do this. Okay, just give you an idea. So one more thing, we can take a look at Schrodinger equations. So once again, it's a second order in space and first order in time. So the second order in space, if you take a look at the spatial derivative, del square, and versus the time derivative. Okay. So without the imaginary number I, if we don't have the imaginary number I, and what do we call this type of a differential equation? So second order derivative in space, del square of the wave function or any function del square equal to, let's say, if the left-hand side has no time derivative, then we call that the type of equation is elliptical, right? And if I was first order derivative in time, we call this is this is the parabolic equation, the parabolic type of equation. And if the left-hand side is a second order derivative in time, partial square, partial t square, then we call it hyperbolic. So in this case, it's a parabolic equation, it's first order in time. Okay. So have you seen this kind of differential equation before without the I? In fact, that is exactly the same as a diffusion equation, right? So without this imaginary number I, it is a diffusion equation. So let's forget about the V of R for a second, just to simplify the differential equation. It's simply first order derivative in time equals to second order derivative in space. Okay. So that's just a diffusion equation. And the prefactors are just the diffusion coefficient that we talk about. But now that in quantum mechanics, the difference between Schrodinger equation and the diffusion equation is Schrodinger equation. Now we have this imaginary number I. So the solution of this wave function psi has the imaginary number in it. Okay. So that's the difference between quantum mechanics and many of the classical physics. Okay. So that's enough about the observations of the Schrodinger equation before we even solve that. So now that let's bypass the how to solve this differential equation a little bit. We'll come back to the specific system given each V of R. How do we solve the differential equation later on? But now let's jump to the second step. So assume that we can solve this differential equation and find out the wave function psi. Then what do we do about this wave function? Okay. So in the case of like hydrogen atom as an example, if you put an electron next to a proton and we're able to solve the Schrodinger equation, find out the wave function of the electron. Okay, it is still a wave function. Then, what if I want to know where's the location of the particle? If you try to measure the location of the electron, where is the electron? Or if we want to know what is the energy of the electron, then what can we get? Okay, so let's move on to that. And this is the done through the so-called Born rule. It's called Born rule. Okay. Okay. Of course, it's named after the physicist Born. So he told us. Oops. This one. Okay. The Born's rule told us that if you already have the wave function for any physical quantity A, so we always use A as the operator of any physical quantity. For any physical quantity A, for any physical quantity A, okay? Then if we perform a measurement on this A, we call, this is the observable. So what can we observe for this physical quantity A? So A can be anything. A can be the energy, the momentum, the location of the particle. So it is, in quantum mechanics, it is represented by an operator. So any physical quantity A is represented operator. And the observable, meaning if we want to observe, if we measure the physical quantity, what we can get. So we put it in this angular bracket A. And so that is equal to the integral of this wave function star. Star means the complex conjugate of the wave function. And put A here and wave function again here. And the three-dimensional case, then we integrate over the entire space. Okay. So why is that? What do I mean by this? So here, the star means a complex conjugate. Write it here. So star means complex conjugate. So for example, if you have a complex number, like Z is equal to A plus BI, right? So here A and B are the real number. And the complex conjugate Z star is just A minus BI, okay? So we flip the sign of the imagined part. Or if the complex number Z is E to the, let's say I something, I phi, is cosine phi plus I sine phi. Then the complex conjugate will be cosine phi minus I sine phi. So it'll be E to the minus I phi. Okay. Let's hold on for a second. Okay, I try to shut down the background noise a little bit. I'm back. Okay, so star is the complex conjugate. So, and A is the operator. So in order to evaluate this integral we first we have to apply. If you look at the sequence of the operation, so first I have to apply A onto this wave function psi, because A is the operator. A is the operator. So first we need to do A times psi, and after that we get a function, and then we times the complex conjugate part of the wave function psi star. So overall, it's a function of space and time, and then we integrate over the entire space. Okay, so it looks rather complicated, but actually, if you look at the meaning of that, it's not it's not that hard to understand. Okay, so if you take a simple example, let's say the two operators we have already talked about, the momentum or energy of the system. Like A is a Hamiltonian, then H psi, what do we get? So we get H psi, then we get energy out. So energy times psi. And then the wave function itself is normalized, and then the psi star times psi integral give you 1. Okay? So simple example, this is nothing but a fancy way to just write down this as A average or H average is equal to E. Okay, so let me give you another example for you to better understand the meaning of that. So let's say if we are interested in the location of the particle. Okay, and let's even simplify that. So in other words, if I'm interested that this A is location of the particle X, and even simpler, we assume the wave function is one-dimensional. So psi is a one-dimensional wave function, psi xt. Okay. It's not to worry about three-dimensional wave function. The system is one dimension. Then, what does this Bohr's law tells us? It means if you want to measure location of the particle X, okay, so X equal to here, we have the psi star and X times psi dx. Okay. So normally, this operator itself is a differential operator. Then we have to apply the derivative onto this wave function psi. But in the case of X, it's location special. Location operator is just the operator, just this variable itself. So X, because it's not a differential operator, then we can move this around. So we can move this X in front of this psi star. Okay. Then psi star times pi is just absolute value squared. So this is just X times psi absolute value square dx. Okay. So what does this mean? So it goes back to this interpretations of the wave function. What does wave function mean in the first place? If you look at this equation, it looks like how do we perform if you know a little bit of a statistics, a little bit of a probability and the statistics, you see if when X is a random variable, then it follows certain distribution psi square, then this integral will give you exact the average value or so-called expectation value of the X. And in fact, indeed, this is our interpretation of the quantum mechanics. So if we can simplify this notation a little bit. So X average equal to X times the probability density of this X dx, where this rho X is equal to psi square or psi star times psi. Okay. So it shows that the wave function square, it's actually a probability density. It's a probability density. Probability density function. So it means that this is, we don't know exactly what the particle is. So this is this is very different from classical physics. In classical physics, let's say, here to limit itself to describe the behavior of an electron. So we can always ask the question, where is the electron, right? If it's particle, then where is the particle? But here we adopt the wave function to describe the behavior of the electron. We have to. This is the only way to describe quantum mechanics. We cannot even answer this simple question, where is the location of the particle? So the entire particle is described by this wave function. Let's say if I draw a wave function. If I draw a wave function, let's say it could be something like this. Okay. It's not a very beautiful picture. Let me draw that again. So it's a smooth function. Maybe let me just draw two peaks. If this is the wave function, and then what does the wave function mean? So the meaning of the wave function lies in the absolute value of the wave function squared. So in fact, that if let this curve to represent the wave function absolute value squared. Okay, and that give us the probability for us to find out the electron or this particle. So in other words, if we measure the location of the particle, okay, so this is the behavior of the particle, and we ask question, where's the particle? First, just ask this question, the particle is described as wave function, so it's everywhere. It's not only at one location before you perform the measurement. But on the other hand, if you perform the measurement, if you measure where the particle is, of course, you end up getting the location at the exact location. But if you can repeat this process many times, you see every time the particle is different. So maybe the first time, if you measure the particle, it happened to be here. Okay, and second time, if you measure the particle, it could be here. So on the x-axis is the location of the particle, and to keep measure that multiple times, you see. So it's more likely. Maybe I should draw multiple times here. So it's more likely for the particles to be detected in these locations. Okay. So if you measure, in other words, if you measure location of the particle, you don't always get the same value. Every time is different. So in the end, quantum mechanics doesn't tell us where exactly the particle is with one measurement. But on the other hand, the wave function tells us the probability for you to find out the particle at certain location x. So the meaning of the wave function lies in its square. So psi square gives us the probability density. So in other words, quantum mechanics is non-deterministic. The wave function itself doesn't mean anything, but the wave function squared tells us the probability of where we can find out the particle. Okay. So, and this is essentially what this Bourne's rule tells us. So if A is the x, then A average, left-hand side is average, will be equal to this x times the probability squared. And you can do this through two ways. So one is if you only have one particle, if you measure that one time, of course, you can only get the location of particle at one location. So the left-hand side of the Bourne's rule is a average. This average can have two meanings. So it can either be one particle you measure multiple times, which if it's one particle, we cannot measure that multiple times. So somehow, if we can restore the system back to the same one, so one system, you can measure this one particle system many times. Then you can, of course, get the average value, okay? And of course, this somehow we have, after measurement, we have to go back, we can return the system to the original state. which is oftentimes not possible. If you only have one particle, we cannot measure one particle many times. Okay. So more often, this is done, you have many identical systems. If we have many identical systems, then we can measure each of them. Since they're identical, it's kind of like repeating the measurement multiple times for the same system. Then we can multiple values out, and the distribution is described by the wave function, and the expectation value noted by this angular bracket, expectation value or the so-called observable can be evaluated by doing this integral. Okay. So this is the so-called Born's rule, and it applies not only to location particle, in fact, to all the quantities. You know, after we got the wave function, then we can ask what is the energy of the system. If you measure the energy of the system, what do we get? You know, Schrodinger equation or quantum mechanics tells us that we don't always get this one number, so we can get multiple values out. This is strange, right? So in the location of the particle is strange because it's not a particle, but the energy is the same. So the energy of the system doesn't have to be one value. You can have multiple values. If you measure the system for the first time, okay, you get E1. And if you measure either identical system or somehow restore the system to original state and measure that again, we get E2. And you can get multiple E1, E2 on all of them, and with a certain probability. And some values may appear more often than the others, just like in this location. So at some location, it's more likely to find the particle. Same thing with the energy. Then we can use this integral to find out the average value, the average energy value you can get. If you can repeat the measure multiple times, then what is the expectation of the value? And that can be done easily by performing this integral. After we have the wave function, then just the operator in between wave function like conjugate and the wave function and perform this integral. So without this operator in the middle, then this start time will be the probability function, okay, psi squared. So there's more to it, and I think this is all we need for now. When we introduce, I will give you more example. You will see more why the Born's rule is written this way. Actually, it's not that difficult to understand, but it's much easier to understand if you want to look at the example. Okay, so this is the Born's rule and the associated. Oh, by the way, so this interpretation of the wave function as a probability density function is the so-called statistical interpretation or Copenhagen interpretation. Statistical or Copenhagen interpretation. Okay, which it was proposed by many of the pioneers of quantum mechanics, like Bohr and Born, actually a bunch of people from Copenhagen. That's why it's called the Copenhagen interpretation. So one interesting thing about the quantum mechanics is, although we have the math to do the calculation, Schrodinger equation and the wave function, and we can use the Born's rule to find out the expectation value of any physical quantity after we know the wave function. But there's no consensus on how do we interpret the wave function. Okay, sounds strange, right? But that is the truth. So we know the math, but we don't know how to interpret the quantum mechanics. Even nowadays, this is still ongoing discussions, and even exists in many of the science fictions or movies. Like one of the recently more adopted interpretations, so-called many word interpretation. So it's just quantum mechanics only select one part of the many possible words. So it shows up in those time travels, etc., etc. So well, in physics, the mostly accepted interpretation of quantum mechanics is this statistical or Copenhagen interpretation. So they basically interpret the wave function. Read that again. So the wave function, they say the wave function itself doesn't have any physical meaning. So the real meaning of the wave function only lies in square. So psi star in psi, and that gives you the probability density. Okay. Of course, this is not easy to accept because the macroscopic world and all the known physics are not like this. So the theory of quantum mechanics as it is now is not deterministic, unlike any other theories we have. Like in Newton's equation, if you know the initial condition, if you know at time zero what the particle, the object is, and its velocity, then we know everything about the system in the future, right? So same thing with the classical electrodynamics. It's Maxwell's equation. It's also second order PDE, but it's a second order in time. If you know the initial condition, like the wave in that case electromagnetic wave, then we know all the behavior of electromagnetic system in the future. But quantum mechanics tells us that okay, we can know the initial condition, we can know the interaction, and we can solve the wave function. But the wave function doesn't tell me exactly what the particle is, because the particle isn't really anywhere. So we only know, the theory only tells us the distribution or the probability that you can find the particle. Okay? So in that way, the theory itself is not very acceptable. Okay, now how can a theory doesn't tell us exactly what we expect to get? So in fact, that question not only bothers us now, it also bothers some of the pioneers of quantum mechanics. So in fact, Schrödinger himself is strongly against this interpretation. Schrödinger formulated the equation, and which allows us to do many calculations very, very accurately. But when he heard about this interpretation, wave function is the probability, he didn't agree. He doesn't think the wave function he formulated only gives the probability. Okay, so that's why I say, if you don't understand quantum mechanics, if you find this interpretation of the wave function square as a probability strange, you're not alone. Schrödinger himself doesn't agree with that. Okay, and there are many times try to further dig out what is happening here. And one obvious interpretation would be, so this theory itself is incomplete. Okay, so the reason that we can only predict the behavior of the particle probabilistically is because we don't know the full theory yet. Okay, so the theory is incomplete, or we haven't discovered some so-called hidden variable. Okay, so for instance, look at these drawings above. A wave function square that gives us the probability of finding this particle. Of course, if you measure what the particle is, you end up getting one right points. So it is one particle at a definite location. The problem is if you measure that again, or if you can repeat the measurement multiple times, we don't always get the same value. So this idea of incompleteness or hidden variable says that so the reason that we don't get the particle at the same time is because we don't know about the measurements. But somehow the measurements affect the behavior of the particle, and we are missing the key variable, which is used to describe this process. That sounds more reasonable. If you want to compare this quantum mechanics to the macroscopic world, and obviously the theory itself is incomplete. In fact, this is exactly what Einstein thought and proposed. So he doesn't agree with the Bohr's interpretation. And in fact, they had a long discussions over many years. There were heated debate between Bohr and Einstein, very interesting history. And of course, neither of them could convince the other. And Einstein, although didn't agree with this interpretation, but ended up made significant contributions to the statistical interpretation. And all the physics later on showed us again, this statistical interpretation is actually correct. So we're not missing any variable. So what is astounding is that now we can even design experiment to test whether there are any hidden variables. This is rigorously quantified by the so-called Bell inequality. And now we can prove that actually Einstein was wrong. So in other words, Bohr and Born's interpretation, Copenhagen interpretation, is correct. It's hard to accept, but it is correct. So not only Einstein hold this idea, the theory is incomplete. So the other people like de Broglie, right, who wrote down the original equation of the wavelength for quantum mechanics, also didn't agree with the statistical interpretation. Okay, so what's strange about this interpretation is before the measurement, because the measurement plays a very important role. So before the measurement, you have the wave function. Right? The wave function, if I draw this wave function again here, the wave function square, it tells you the probability of finding the particle. But after you do the measurement, so if you after you do the measurement, so all of a sudden we don't have the wave function anymore. So the particle will be exactly determined at one point. Okay? So in other words, we use this word collapse. So all of a sudden, the wave function collapse to one singular point. So there is something strange about this measurement. Okay. So and how exactly the measurement affects the wave function is a much deeper question. It's not appropriate to talk about that now. Only after we are able to do quantum mechanics, then we can come back to revisit this question. So for now, just consider measurement as the measurement we do in our labs or we say in common. Okay. So that's the interpretation. So now that the probability, so psi square is the probability, then we can have a, oops. Then tells us that this wave function square must satisfy this normalization. Normal. So normalization. So meaning the wave function square, it's one dimension, then let's say it's one dimensional, dx then equal to 1. So because this psi square tells us the probability, and if you look everywhere, then you always be able to find the particle. So integrate this wave function square, we should get 1. So the wave function itself is normalized. Okay. So this is actually related to some of the other problems of the wave function. So not only so the wave function itself, the wave function itself has really no meaning. Okay. So we did everything we can, formulate the Schrodinger equation and solve the equation, find out the wave function. Then we say the wave function itself has no meaning. It's even worse if you look at the Schrodinger equation itself. to look at the Schrodinger equation itself, you can keep that in mind. So left-hand side is I h bar partial t psi, and right-hand side is the space dependent. Let me just write down h here, Hamiltonian psi. Okay. So it's operator, another operator times psi. So this wave function itself has an undetermined scaling factor. So if psi is a solution, if you scale the psi multiple times, like constant times, then it's still a solution. So without this normalization above that, we cannot find out what is the wave function. So this wave function, this normalization condition, get rid of the one prefactor of the wave function. So even worse, let's say you already have a psi. So here, okay. Let me write this down. So if you write down this psi, change this psi to some constant times psi, then C times psi is still a solution of the original differential equation. Right. So even worse, if you change the psi, not only a constant, but we time a factor, exponential times I alpha, right? It's a very different wave function. We change the phase of the wave. Okay. Even though the wave function is different, but now if you take a look at the wave function square, say absolute value square, that is the same. So this remains the same. So the wave function is not even unique. So we use the wave function to describe the system. It's not even unique. Okay. So that is true. And so those are a few of the problems of quantum mechanics, and there are really some ongoing studies, like what determines this phase. So, but for us, from a practical perspective, it doesn't really matter much because we don't really care about the wave function. As long as the wave function square doesn't change, then we can just use it to determine the probability of finding the particle. Okay. So then, what else does this interpretation require us? So the wave function square tells us probability. Then we require the wave function to be continuous and smooth. Let's write it down here. Continuity and smoothness. Smoothness of the wave function psi. Okay, so in other words, we require two conditions. We require the wave function itself is continuous. Okay, and second is we require the derivative. So the one dimension is ddx. It's also continuous. So with one caveat, except at infinite potential. Okay, so what do I mean by that? So first, let's say if the wave function is not continuous, what's going to happen? So if the wave function is not continuous, then if you take the derivative of the wave function, then we get infinity. So what is the derivative of the wave function? So take the derivative in space, take minus h bar del. Okay. Let me write it down. In fact, so if psi is not continuous, then it's minus h bar del psi would diverge, right? diverges. So what is that? So that's the momentum, right? So if the wave function is not continuous, then we get infinite momentum. So that's why wave function must be continuous. The same thing for the second. So if it's d phi dx is not continuous, if the wave function space derivative is not continuous, then the kinetic energy would be p squared over 2m, so h bar squared over 2m del square psi would diverge. Okay? So get infinite energy. So that's why we say here, so this is not allowed unless the energy itself is already infinite. So if you put particle in some infinite potential, then this ddx doesn't have to be continuous. So in other words, the wave function doesn't have to be smooth. But in either cases, the wave function itself must be continuous, and whether it's smooth or not depends on whether we are talking about infinite potential. So in normal case, we don't have infinite potential, then the wave function itself is both continuous and smooth. So we're going to use these conditions, especially at the boundaries, so that we can stitch the different pieces of wave functions together. Okay, so I think that's all we need for the basic understanding quantum mechanics. So next time, we're going to solve one example. Okay. Stop, and thank you very much. I'll see you on Wednesday.